Hi, this is Abe here, and we're going to be talking about antiderivatives for polynomials today. So, an antiderivative is just the opposite of a derivative, right? And it's also useful to find areas under graphs. So, given that very brief intro, let's very quickly get into it. So, firstly, just a little bit of notation. You'll know that an antiderivative is written like this. Capital F of x, which is basically the integral of f of x dx. So what all this means is that if you get given a function f of x and you want to find its antiderivative, what you do is you do this thing called an integral, and you have to shut this integral with a dx. And if you do this, you'll come out with f of x. Capital F of x, and capital F of x is the antiderivative for f of x. Confusing, huh? Or alternately, you can be asked, say, if you've been given a derivative and you want to find the original function, well, what you do is the same thing. Integral of f dashed of x, which is a derivative, and if you do that, you come out with f of x. Great, which is the original function. Alright, so now the big question, how do you actually go about doing this squiggly integral thing? Well, that's what we're going to show you today on polynomials. So, for polynomials, it's really simple. Really, really simple. All it says is this, right? So you know polynomial is x to some power. So we want the integral of x to some power dx. And what does it come out to? Well, the rule goes like this. You start with, so there's got to be an x in there. Good start. Now you increase the power by 1, n plus 1, and divide by the new power. That's it. Oh, and you do this plus c on the end. This c just means some constant. Because remember, if you want to get back to the original function, you would differentiate, and when you differentiate, that constant disappears. So it doesn't matter what that constant is, but we just got to say there's a constant. So that's what the c does. And that's it. Antiderivatives for polynomials, pretty much. Let's just run through a really, really fast example. Really, really quickly. So for instance, let's say you've been asked to find the integral, or the antiderivative, of 4x cubed plus 7. Right? You've been asked to find that. Okay, so what do? Well, you can split this up and you can do each term separately. So it goes like this. You say, alright, 4 still stays as 4. Now x is to the power of 3, so you want to increase the power by 1. So now we've got x to the power of 4. Divide by the new power, which is 4. Gee, we've got a lot of 4s here. Not good if you're Chinese and superstitious. Alright, so there's that part. And then, the next term is 7. Now, I want you to note something, that 7 is the same as 7x to the power of 0. Now, you'll know that x to the power of 0, or anything to the power of 0, is 1. So 7 is just 7x to the 0. So this works on constants too. So what you can do is increase the power of x to 0 by 1. You get x to the power of 1, divide by the new power. Oh, look, it's x. So 7 just becomes 7x. And that's it. And remember your little plus c. So yeah, that's it. Very simple, isn't it? So next, we're just going to do a slightly more complex example, which is shown as follows. So what happens if you get a polynomial, but it's expressed this way? Say ax plus b to the power of n, like that. It's still a polynomial, right? You can expand that out, you'll get something, and it'll be, x to the power of something plus x to the power of something else, etc. So that's really great. But how do you deal with this? So again, I'm just going to share with you the rule. And the way this is dealt with is really simple again. So what you do is you take that whole bracket, ax plus b, and you increase the power on it by 1. This is looking kind of familiar, to n plus 1. And you divide by the new power, n plus 1. Looking familiar so far. The only trick is you also need to divide by the coefficient of x in the bracket above. So a in this case. And remember your plus c on the end. And that's it. Simple, huh? So basically, this is really useful if you have a question that looks like this. So let's say you had to do something that said, alright, find me the antiderivative of 5x plus 7 to the power of 6. Now, you could expand that and then collect terms and then antidifferentiate that. But given this formula that we have, we don't need to do that. So this is what we're going to do instead. We'll just follow this. So what's going to happen? 5x plus 7, that doesn't change. Increase the power on it by 1, so that now becomes 7. Now you got to divide by the new power and divide by the coefficient of x, which is 5. So quite simply, you're going to come out with 5x plus 7 to the power of 7 over 35, and remember your plus c. And that's it. Actually, not quite. We've got our little formula here, which is what we just saw before, but what if n equals negative 1? Now on first glance you might think, well, it's supposed to work, right? But look at this. In our answer we've got an n plus 1 just over here. So if we put n equals negative 1, we're going to divide by 0, and it's going to look really, really bad for all parties involved. So actually this is what happens if n equals negative 1. So you'll agree that if n were to equal negative 1, then we'd have an integral that looks kind of like this. Integral of, now you've got ax plus b to the negative 1, right? Negative 1 just means 1 on ax plus b dx, and that actually rather magically comes out as 1 on a log to the base e ax plus b, like that. And then that's it. So the straight lines are modulus signs, you should know them already, and that's what it comes out to be. So there, we've covered all scenarios. So a very, very quick example. Look, if you've got integral of, let's say, 2x plus 4, then you'd go, alright, well, then in our case a is 2, so you just go half log to the base e of 2x plus 4. Done. Alright, so now we've covered all the scenarios we can. This is antidifferentiating polynomials. I hope you enjoyed it. See you again next time.